In this video, I'd like to talk you through how to use OpenOChem to display Lewis structures. The purpose of this video is not actually to teach you how to draw Lewis structures, but rather how to use the features of OpenOChem to display the Lewis structures. The OpenOChem platform is highly powerful, but it's mainly a tool to draw organic structures. It works quite effectively, though, for Lewis structures. One of the things that I really encourage you to do, especially for more complex examples, is to draw the Lewis structure on paper. Like, go through your set of rules on paper, and then once you've arrived at the Lewis structure, then draw it into OpenOChem. There's just some features that make it a little harder to just follow the rules, and I will illustrate that as I go along. I am using the Chem 112 Homework 10 as a template for showing you how to use the OpenOChem platform to draw Lewis structures. So in a sense, I'm doing some of your homework for you. I'm starting with the iodine difluoride cation. So what we do is, and note you've got a menu bar on the left side here and different things can be selected. I'm going to select the plus and then the CH4 group down here, which is called the methane. This is just to get something on the draw screen. I then want to change that CH4 to the iodine, as the iodine is the central atom. To do this, I'm going to come over to this C. Now this C looks like it should just be putting in a carbon, but it's actually called the atom tool. So I click on this, click here, and then I can change that CH4 to a whole bunch of different things. So I'm going to change it to the iodine. But if you don't find the atom that you're looking for, you can click here under More, and then you've got the whole periodic table to work from. So once again, I'm going to click here. I'm going to change this to the iodine. Now, of course, the first step in actually drawing a Lewis structure is to count the total number of valence electrons. And in this particular case, we would have had 7 from the iodine, 14 from the fluorine, so that would have been 21, minus 1 because of the plus charge. So technically we need to put out those 20 electrons. And we know that we also need a skeleton. So I'm clicking on this bond tool, and then I'm going to click on the I, and note that there was a hydrogen there, and that's just so that the iodine had the proper valency. So then I click again, and again that H shows up again for the iodine to have the proper valency. Now, what I just did here is, away from the plus sign, I clicked on this arrow because what I want to do is expand these bonds. So again, I click on this arrow, then click on the edge, and then dragging, I'm going to pull this out. It just makes it a little easier. So click here and then pull out as such. And then now on the ends, I'm going to put fluorines. So again, the plus sign, the C, and then click here, and I'm going to put a fluorine. And then I'm going to put a fluorine. Now, if you did this on paper, the idea is that then you'd put out enough electrons to give an octet to everything. Where the electrons are found are under the plus minus here. So here's the lone pair of electrons, and I'm going to click 1, 2, 3 times. So I've just put out 3 lone pairs. Now, unfortunately, the lone pairs are often put out somewhat far from the atom. So again, I click on this arrow sign, then click on the lone pair, and I just drag it a little closer. Click here, drag it a little closer. Click here, drag it a little closer. And then let's put out the other lone pairs of electrons. So over here, 3 lone pairs. Maybe just position them a little more closely, especially for larger atoms. It'll be important, larger molecules. It'll be important to do this. Okay, let's bring that a little closer. Now, you may be still wondering about this H and what are we going to do? We don't have any H's. Well, it all will work out. Note that I still need to put out, because I've only put out 16 electrons, 2 more lone pairs. And of course, they're going to go on the iodine. So put them on the iodine. That still doesn't get rid of that hydrogen. But one of the things that you may have noticed is that there's a formal charge. And just ignore the hydrogen for a minute. This iodine normally would have 7 electrons. And ignoring this hydrogen, we've got 2, 4, and then it owns half of these things, so it owns 6 electrons. So that iodine, ignoring the hydrogen, would have a positive formal charge. So now I click over here, plus, minus, and then click on the plus, and then click on the iodine, and then there we go. So the reason why I suggest that you essentially draw the Lewis structure on paper is you would have come up with this, and then effectively you're just translating what's on paper onto the draw platform right here. So I check my response, and indeed it's correct. I'd like to do just a few more so that you can see some of the things that you may encounter. So for instance, I'm going to come a little bit further along. And so I just did the iodine difluoride cation. I come a little bit further along, and I find the carbonate anion. Again, I really encourage you to produce this on paper. And if you did, you would know that carbon's the central atom. You've got 3 oxygens surrounding. In terms of counting the total number of valence electrons, you would need 24. And then you would find that in order to give an octet to everything, you actually would have needed 26 electrons. So that tells you that you need a double bond. So kind of keep all of that in mind. I'm now going to try to draw this particular structure. So I got to include 1 double bond coming off of that carbon. So to begin, I'm going to actually begin with the CH4. And note, look what happens when I try to put a carbon on here. All right, it just remains as a CH4. In a sense, the program knows that carbon can't just sit there by itself. If you're going to write the C, well, then you need 4 hydrogens. If I start putting bonds off of here, I don't want you to be alarmed in that this is meant to be a draw platform, if you will, for organic molecules. And we often use this bond line notation where we understand that a carbon is here, a carbon's on the end, a carbon's on the end, a carbon's on the end, and that the appropriate number of hydrogens are present. Now, it might be good for you to actually see the carbon. So again, I clicked on this arrow here. I click in the middle. And then on the end, I'm going to show label. Now, you don't need to do this very much, but for that carbon, yes, this is what you would need to do. So it automatically put a hydrogen in, again, because carbon needs to be making 4 bonds. This hydrogen will disappear as we start to put together the molecule. Again, I want to make the bonds longer so that it's easier to see what's going on. So make that longer, make this longer, and then I put out my oxygens. So click on the plus, and I could use the atom tool. So I click here and click on the end, and I can choose oxygen like this. But I can also come over here and select the oxygen in the template or the menu down at the bottom, and then click on the end here. Yeah, puts an oxygen, puts an oxygen. But you can see it also includes the hydrogen. It's because neutral oxygen is making 2 bonds, in this case 1 to the carbon, 1 to the hydrogen. But we want to alter this, and it all works out given what the formal charges are. So as you know, we were supposed to put out 24 electrons and still have an octet for everything, where one of them is a double bond. So here's the double bond feature. So I'm going to put the double bond there. Right? So you would have seen this on paper, and you would have seen that you then put out 2 lone pairs here. Again, they're kind of far from the atom, so I'm just going to bring them a little closer. Okay. And then you would have put out a total of 3 lone pairs around each of these other oxygens. So again, you would have done this on paper. And because these oxygens, ignoring the hydrogen, is in fact owning 7 electrons. So it owns all of those lone pairs plus half of the bonding pair. And oxygen normally has only 6 electrons. There's a negative formal charge there. So I click on the negative sign, click here. And so you can see that that works out. That there is, of course, no hydrogen because that oxygen has a negative formal charge. Okay, so there we are. I will do the same thing on the other side. So let's put out the lone pairs. Lone pair, lone pair, lone pair. And we have a negative formal charge. So put that out. And so that essentially is one of the resonance forms. I think it's hard to just go through the rules using OpenOChem for some of these more complex structures, especially with this tendency on carbons, oxygens, and nitrogens that OpenOChem will sort of automatically input a hydrogen. So it would be better that you come up with this on paper and then draw it. Now note, we have used a total of 24 electrons. So in a sense, 8 around this oxygen, 8 around this oxygen, 8 around this oxygen. The carbon has an octet. All the oxygens have an octet. We've got 2 formal charges, so it adds up to the total charge. So indeed, this is the correct answer. And there would be 2 other resonance forms where the double bond is over on the left-hand side and the double bond is at the bottom here. I only want you to draw one of the resonance forms. So I'd like to run through one more structure, and it's just because it's a larger one, and I'd like to show you how you need to be paying attention how you're putting out the lone pairs. So it's further along here. It's, in fact, yes, this one. So this is our sulfur pentachloride cation. And so we're going to start off with the plus selected. We're going to put our CH4 group out. So then I click on the plus. I click on my C here. I click in the middle, and I want to put a sulfur group. So here's my sulfur right here. So I click on the sulfur. And you can see automatically it puts in the hydrogens just so that, sulfur's not breaking the octet rule. But that'll all get fixed when I start putting out bonds. And I've got 5 bonds to the chlorines. So 1, 2, 3, 4, 5. Don't worry about the hydrogen. That will get fixed as we finish. So once again, I click on this arrow here, and I want to make the bonds longer, especially with this more complex molecule. So let's just pull these out. Okay. And again, if I were to have counted all the electrons, so 5 times 7 is 35, plus the 6 from sulfur, that would be 41, but minus 1 because of the plus charge. So I need to put out 40 electrons. I want to put out the chlorine on each of these ends. So click on the carbon, click on the atom tool at the bottom here, and then on each of these ends, I insert a Cl, I insert a Cl, insert a Cl. As I keep mentioning, it would be best that you draw these on paper, and then you're simply trying to reproduce them here in OpenOChem so that you can see if you've done this correctly. So I've spread these guys out. I'm not trying to show any particular geometry. I just want to have enough room. I would give an octet to everything, and you can see that indeed sulfur will be breaking the octet rule. So we need to put out 3 lone pairs around this chlorine. You can see they're all over the place. So let's just bring them closer, and that way we won't get any of the lone pairs mixed up between the different atoms. Again, I'm going to put out 3 lone pairs. So there they are. And you can see that they're pretty close to some other atoms. So bring this closer. Bring these guys closer. These guys closer. Let's do it again. Now I'm picking some more challenging examples. Many of the examples that I have asked you to do, they're smaller molecules and they don't require arranging all these lone pairs like this. But I want you to see what to do when you do have to arrange them so that you're able to draw the Lewis structure, but you don't end up having a lone pair feel like it's associated with an atom that it's not actually associated with. And we have one more chlorine to work with. So then lone pair, lone pair, lone pair. In fact, I think they're fine, but I'm just going to bring them a little closer. So at this stage, actually, what I have just done is I have put out the 40 electrons. Now let's ignore the hydrogen. So unless explicitly we're supposed to include the hydrogen, it shouldn't be there. And if you count the total number of electrons that this sulfur owns, forget the hydrogen, it would own half of each of the bonding pairs. So that would be 5 electrons. Sulfur normally has 6. And therefore, this sulfur would have a positive formal charge. All the chlorines don't have a formal charge. So we click on the plus minus here, click on the plus, and then click here. And indeed, you can see that that takes care of the hydrogen. So it's a little extra work in putting this together to make sure that the lone pairs don't overlap. And I keep repeating myself, I encourage you to do this on paper and then actually draw it out in OpenOCam. So I check my response, and sure enough, it is correct. So I'm hoping this video has helped you see the approach to drawing Lewis structures. If you're getting stuck, please don't waste your time. Come and see me, email me, let me help you. Again, the OpenOCam platform, it's to give you ample practice in drawing Lewis structures so that you get the immediate feedback and make sure that you are on the right track.